Okay, so now we want to look at hypothesis testing for a single proportion. And again, I will point out that there are actually two proportions here. But this is section 3.1, and we're looking at hypothesis testing for a single proportion. And we'll go back to the free throw example in our 12 and 36 cases. So, in this case, yeah, I have data for a proportion. We had n equal 48 free throws, and S was 36 baskets, okay, or successes, and F was 12 misses. Okay, so that's your data, and suppose that the goal for the team, let's say the goal is 80% free throws, or on free throws. Okay, so maybe my goal is 80%. And so the question here, sort of my research question, I guess. Research question is, did the team make it? Well, now on the surface, no, of course they didn't. They were 75%. But the real question is, then, is there evidence to say the team is not at 80%? Because again, the team might be at 80%, but they had an off week, and so they were 75%. And so, it's not as simple a question as just going, oh, well, no, they wanted 80%, they got 75. Well, do we actually have evidence to say the team is not truly at 80%? Well, I don't know. We'll have to figure that out. And so we use a hypothesis test. And in this case, our goal is the null hypothesis. Because again, the null hypothesis is the population. Well, when you look at our question and our goal and so forth, our goal is 80%. And our question is, did the team make it to 80%? Now, the team actually didn't. The data, don't indicate that it at face value. But the question is, well, statistically, could we have sampled from a population that has 80% success, sampled 48 times and gotten 75? How likely is that? And so that's our hypothesis test. Our H0 is that our proportion is 0.80. Now we're going to do two-sided tests. So our alternative here is that it is not. Oops, I was writing down the 75%. Right, so it's either 80% or it's not 80%. Your null hypothesis should always be about equality, a single case, a one particular case, and then the alternate is typically everything else. And so, so we want to run this hypothesis test. Well, the hypothesis test is actually very akin to the confidence interval. You can get slightly different results. You could, for instance, make the confidence interval, and I don't remember what our confidence interval went, I think, all the way up to 0.87 or something like that. And so I am really sure that we are going to fail to reject the null hypothesis. Okay, and the reason for that is when we made our confidence interval, I think the confidence interval for this data was something like 0.6, if I can remember, maybe like 6.775, and it went up to 0.8. 725 or something like that. I don't know if that's quite right. 1, 2. No, I think this was a 2. Okay. So, but the important part is that 0.8 is in there. Okay. Well, so if my null hypothesis value is inside the confidence interval, it will rarely be the case that we will be able to reject the null hypothesis. Okay? Because remember, we did a confidence interval and we said, hey, the right answer is somewhere between 62 point something percent and 87 point something percent. Well, 80%'s within that. And so we were 95% confident at that point with that confidence interval that 80% was in the interval. Oh, okay. So we should still be on that side of things that yeah, you know, the 80% could have been the population's percentage. And so, you know, it would be a very, very rare case where then doing this hypothesis test, we would be able to reject the null hypothesis. So I will not be surprised when we get a very high p-value. Not p value. Okay. So here is our hypothesis test we're going to run, and then we're going to look at, well, how do we calculate a p-value for it, and so we have this, but I really quickly just want to point out we really do have two proportions. So another way to look at this could be a null hypothesis that's more specific, is that, you know, the probability of successes is equal to 0.80, and the probability of failures is equal to 0.20. Okay, and then the alternate is that at least one of PS and PF is wrong. Okay, when think about those two, these are equivalent statements. They're equivalent hypotheses, right? Because if my probability of success is 0.8, then my probability of failure had to be 0.2. And so that's the case. And then if the probability of success is not 0.8, well, then at least one of them is wrong. Okay, actually both will be wrong, but typically the way it's said is at least one is wrong. And so I just want to point this out for the later stuff on chi-square goodness of fit test, is that when we do this hypothesis test up here, we could have just as easily done this one down here with a goodness of fit. Okay, and so, you know, a single proportion again is really two proportions for a given variable, right? The variable is the outcome of the free throws, and it's either a success or a failure. So, okay, now on to the hypothesis test. Well, we need to determine what's the probability that we could get our data or worse. So it would be, we want to look at the probability that for us, z, the absolute value of z, okay, so the standard normal distribution, is bigger than what we got in our data. Okay, so we have to get this in terms of standard deviations because it's a standard normal distribution. And so I need to take my 0.8 minus my data. Okay, that's how far off we were. And then, and actually, we write it the other way around. And so I'll use absolute values. 0.75 minus 0.8. And then divided by our standard error. Well, that standard error in this case, now, when we did and this is why you could get, rarely you can get different answers from the confidence interval versus the hypothesis test, is that since we have hypothesized the population has a probability of 0.8 for success, we would use 0.8 in here, 1 minus 0.8, and then divided by our 48. Okay, so instead of 0.75 that we did for our standard error. So what we're doing is we're taking our data, so p hat minus p, our hypothesized value, or actually you would tend to call that actual number 0.8 p0, and divided by then the standard error. And that is to get a standard normal distribution, and we can look up that probability, and that's what we do. Okay, so I have those numbers. Again, I'm not expecting you to do these calculations. You can go here, and here's a test of a single proportion. And so what is our P0? Well, in our case, it was 0.8. That was our hypothesized value. And then remember to adjust successes, failures, and n. Okay, so we had 36 successes, 12 failures, and n then was 48. And what this does is, again, like with the confidence interval, it gives me my p hat, and it gives me my p-value. Now, here are all the calculations for the graph and so forth. And I can look here and kind of see what's going on. The dotted line is the 95% line. This has 0.025 out here to the right and 0.025 to the left. But you see, this is just showing us a picture of this, how this p-value is. it's way bigger than 0.05, and so we're way inside with our areas. I think the green area is the actual calculated area, but it's a two-sided test, so we take both sides of the area, and we see that our data, see there's 0.7 and then 0.75, our data was all out here from 0.8, or equally likely we could have been above and been out here, but we get a p-value of 0.3864, so we definitely fail to reject the null hypothesis. And so if we come back here, we get our p-value, this probability, forget that for the moment, this probability is equal to, oh now I forgot, 0.3 something, 0.386 we'll call it. That probability is 0.386, which is definitely bigger than 0.05, and so we fail to reject H0, okay, that P equals 0.8, and so what that means is we don't have evidence. Now notice I'm putting this in terms of the alternate. We don't have evidence to say the team isn't at 80%. Now they might not be. It's, I mean, the little bit of evidence we have, we kind of went, well, no, they're below. They aren't doing as well as we'd like. But statistically speaking, assuming our population really is 0.8, the team really is at 0.8, well then it turns out they had a, whatever that was, almost a 40% chance of only getting 75% of their free throws out of 48 tries. A 38 to 40% chance. That's a pretty big chance. And so, although if I'm the coach, I still want to work on free throws and all that, statistically, I can't say the team's not at our goal. Okay? I will need more data to know whether or not the team truly is at our goal. Okay? But right now, because we failed to reject H0, we don't have evidence to go with the alternative, is what we're saying. Okay? So we don't know, so failing to reject H0 doesn't mean H0 is true. Right? We don't usually come up with that conclusion. Usually the conclusion is, well, we don't have evidence to say it's not true. A couple of negatives in there, right? We don't have evidence, so there's one negative. We don't have evidence to say the team is not, okay, there's another negative at 80%. And so the double negative is sort of like saying it's true, right? One if you think of math, right, two negatives multiplied together or in succession like that makes a positive. But remember, we tend to frame things in terms of the alternate, and so we don't have evidence to say that H0 is false. But that's not exactly the same thing as saying we do have evidence to say it's true. Okay? And so that is this idea of a test of a single proportion, but notice that's really could be thought of as two proportions, so just kind of remember that as you look at problems. You could always think of it as these two complementary proportions. Okay, we'll call that done.